Hello, this is Yanofsky. We're doing theoretical computer science. We're up to chapter 7. This is the second video of chapter 7. Okay, so what are we talking about? We're talking about as follows. We're talking about time complexity and how much time a problem takes. Okay, we're not talking about how much time an algorithm takes. We're talking how much time a problem takes. So we had the following example. I just want to review the end of last class. We looked at this language, O to the k, 1 to the k. And here's the problem of this language. Give it an input, tell if it's in this language or not in this language. Okay? And we can talk about k greater than or equal to 1 or 0. Okay? Again, here's the problem. Given an input, tell if it's in this language or not in this language. And the first thing we did was we showed, you know what? This language can be determined by an algorithm that takes n squared. Okay? And that was a very simple algorithm. You go back and forth, back and forth. How many times you go back and forth? N over 2 times. So it's about n squared. Okay? But then we saw, no, we can do better. And we said, you know what? It's not only there, but it's also in time of n log n. We found a cleverer argument, chopping out every other one's, checking odd and even, and we saw it's in here. Now this set is a subset of this set. So here's what we have. We have the set of all languages, okay, and we have Turing decidable languages, and that's what we're dealing with. And we saw here is time of n squared, and we showed, hey, look, this language is in here. But then we said, no, we can even do better. We could say it's in time of n log n. That little box. So here is where O to the k, 1 to the k is. Okay, so it's in that little inner circle. Okay, so that was a very nice thing. And then we said, you know what? We can even do better. Okay, if we allow more than one tape. Okay, so what I'd like to do now is focus in on that little theorem about how we can do better if we allow more than one tape. Okay, so there's a theorem. And it goes as follows. Okay. Theorem. Let t of n be a function where t of n is greater than or equal to n. That's just a standard. That's a requirement, but it's an easily filled requirement. N squared, n log n. All those things are more than n, so it's not hard. Okay. Then every tn time multi-tape Turing machine has an equivalent. Let me just write it, then I'll explain what it is. O of t of n squared time single tape Turing machine. Okay, let me just read. Let Tn be a function where t of n is greater than n, greater than or equal to, then every tn time multi-tape Turing machine has an equivalent O of t of n squared time single tape Turing machine. Now what do I mean by equivalent? I mean whatever the multi-tape machine can do, the single tape Turing machine can do. Okay? So what this is showing is whatever you can do with a many tapes, you could do with a single tape also, okay? But it'll take a lot of time, okay? And I just want to go through the idea of the proof. The idea of the proof is as follows. Let's say you have 3 tapes, okay? And this tape has things like this, and then a bunch of blank spaces. And this tape has things like this, and then a bunch of blank spaces. And this tape has things like this. And you know what? Sorry, don't want to use that symbol. Don't want to use that symbol. And this tape has things like this. I'm making up these symbols as I go along. Things like that. Okay? Well, guess what? I can mimic such a 3-tape Turing machine with a single Turing machine. And here's what it will be on the single Turing machine. I'll copy out this and then put a number sign. A number sign means finish with that tape. Now we're doing the next tape. Then here will be something like this, and then we're going to have a number sign. And here will be something like this, the exact same symbols, something like this, and then there'll be a number sign. Okay? So I could put all 3 tapes on one tape. But remember, all 3 of these tapes have eyes that are looking at it. So I can describe which eye it's looking at by putting a dot over that symbol. So here's that symbol. I'm going to put a dot over that symbol. He's looking at this symbol. We'll put a dot over that symbol. Okay. Now this single tape Turing machine has all the information of this 3-tape Turing machine. And the idea is as follows. What this tape will do is read across, look for all the dotted elements. Okay. Go back here, look at the rules. What happens if you're looking here in the first tape, you're looking here at the second tape, you're looking here at the third tape. So it's going to find out what the 3 dots are, make some look up in the rules here what to do then, and then we'll actually do them. So they might change this to this symbol and move the eye that way. And then change this to some other symbol and move the eye this way. And change this symbol to something else and move the symbol that way. Okay? So it's going to be going back and forth, looking at all the dotted symbols. Each time it looks at the dotted symbols, checks what the rule to do and does it. Great. But what's a bad thing that can happen? One of the bad things that can happen is it could be pointing here, or it could be pointing here, let's say, and then say move to the right. So it would be pointing here, and then it would say move to the right. Now over here to the right is an infinite sequence of blanks. Here to the right there's no room. What to do? Okay, so watch what it has to do. What it has to do is then move all the way over here to the last number sign. Move this number sign 1 space over. Move this symbol 1 space over. Move this symbol 1 space over. Move that symbol 1 space over. Move that symbol 1 space over. Keep on moving all the symbols 1 space over till you move this number sign 1 space over. Then you're going to have extra room here. And you can do whatever he tells you to do over there. Now that is called bad space management. Okay, that's stupid bad space management. But it works. Okay, question. How long does it take to do this mimicking? Okay, and the answer is, well, how long does this take? If this computation is going to take t of n time, then what's the worst thing that can happen for this single tape Turing machine? The worst thing that can happen for the single tape Turing machine is every single time it's going to want to move over into a barrier. And so every single time it's going to have to go all the way over here, that's n. Okay, for every single movement, it's going to have to move all the way across the entire thing and move everything over. Okay, that's 2n or 3n, etc., etc. But the point is, you could do that for every single tn step, which means that for every tn step, you're going to have to move tn things. You're going to have to move tn things. That's where, for every single thing, it's going to have to move tn squared times. So, let's just go through it. Technical details, you're going to read it in the book very carefully. Technical details. But the point is, whatever can be done by a K-tape Turing machine can also be done by a single-tape Turing machine, but it's going to take the amount of time that it did here, it's going to take square amount of time here. Sounds good. Okay, great. Okay, now, next. So this was one of those, in section 3.2, I think we had variations on a Turing machine, variations of Turing machines. This was one variation. What about nondeterminism? That was another variation that we had. Okay, so there's a theorem about that too, and it's in the book. Okay, let's erase this. But now we're not talking about, the theorem is almost the same in a certain sense. Well, similar. But now we're not talking about souped up Turing machines which have multi-tapes. Now we're talking about nondeterminism. And we talked about nondeterminism, how it does more than one thing at one time. Okay? So, let's look at this theorem. Let Tn be a function where T of n is greater than n, then every Tn time nondeterministic single tape Turing machine has an equivalent two to the T of n. I'm going to put an O over there. Time deterministic single tape Turing machine. Okay, so beforehand we were talking about multi-tape versus single tape. Now we're talking about non-determinism versus determinism. So if you have a Tn time non-deterministic Turing machine, then it has an equivalent. Equivalent means it's just as powerful. 2 to the T of n time deterministic single tape Turing machine. Okay, so non-determinism, change it into determinism. Let me just give you the proof. We mentioned the proof, but I'm going to be a little bit more careful here. So if you have a deterministic Turing machine, basically it goes as follows. Here's your starting state. Then you do one operation. Then you do another operation. Then you do another operation. Then you do another operation. Dot, 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 dot. Then you do another operation, then you come to accepting or rejecting state. Non-determinism is as follows. I'm start at the starting state, but I could do this, I could do this, or I could do this. I could do this, 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 I could do these two. For this state, I can do this. This state I can do nothing. This state I can do two things. This state I can do three things. This state I can do nothing. This state I can do one thing. This state I can do three things. This state I can do three things. Keep on going. And when is such a computation accepted? Well, if one of these stages is Q accept, then the original word is accepted. So you have to go through all of it. Great. So this is the way a non-deterministic machine works. I'd like to show you how a deterministic machine can mimic a non-deterministic machine. It's very simple. What you have is a 3-tape Turing machine. Okay, now I know it says single tape, but you'll worry about that because we know how to change a multi-tape into a Turing tape. Okay, the one tape is going to be the input. One tape is going to be the address, and one tape is going to be the work that you do. Okay? And what you're going to do is you're going to deterministically put the input on, see what the address is, and you're going to search for a Q accept. Let me show you what it means to search for something. You're going to do what's called a breadth first search along this thing. So you're going to try this thing. You're going to see if it works. If not, you're going to try this address, then you're going to try this address, then you're going to try this address. Then you're going to try this address, 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 this. Okay, then you're going to try this, etc., etc. Okay, each time, if you find a Q accept, you say, yay, I found it. I found what I'm looking for. If not, you keep on going. Here you're going to you're going to systematically go through the addresses. And here, for every single address you find, you're going to do the following thing. You're going to put the input. You're going to see, okay, what is this address? What does this mean? The third thing, whatever. You're going to somehow systematically do it. You're going to work out the whole tape with that thing. And every single time you're going to do this. Great. Question, how big is this tree? Answer, 2 to the t of n. Okay, a little bit, I'm fudging the details here, a little bit 2 to the t of n, but it's 2 to the t of n. Exponential growth. This tree grows through exponential growth. Okay, but the point is a deterministic machine can do what a non-deterministic machine does in exponential amount of growth. Okay, stop. The main point is that this this non-deterministic machine can be done in deterministic time. Okay, just want to talk about how much work can be done with this, how much work it takes. Well, it depends on how big it is. So we let B equal maximum number of branches. Now you have to understand, the rules that describe this non-deterministic machine is a finite set of rules. So it's going to say, do this, do this, do this, do this. The largest amount is B, let's say. Okay? And what we have is as follows. If B equals max number of branches, then the tree is, if the tree goes down t of n steps, then the tree is B to the B to the t of n. Okay? B to the t of n. In other words, that's how many steps it has to do in order to do this. It could be +1, could be -1, but that's how many steps it has to be done. Okay, so B to the 2n. Okay, I just want to write that in terms of this. This is O of 2 to the t of n. Okay. Although this has a bigger base of the exponent, but it's to a reasonable thing, it's O of t of n. Let me just explain to you why. Okay, so let me just do this. B of t of n is equal to 2 to the log base 2 of B times t of n. Okay. Let's just raise this. 2 raised to the log base 2 of the, that's B to the t of n. That's exactly that. So this, it becomes B, and that's t of n. Okay, and so this is, maybe I shouldn't have written it like this. Sorry. The main point is that's a constant. That doesn't change. Okay, so maybe I shouldn't have written it like this. Maybe I should have written it as 2 to the O of t of n. Maybe that's more exact. Okay, great. Anyways, let's just recap. Multi-tape to single tape, that is an n squared operation. That squares the amount of the length that you have to do. Non-deterministic to deterministic, that is exponential. Okay, exponential. Doesn't matter how you look at the exponential. Okay, now, main point. Let's not talk about t of n. T of n is any function. Let's talk about p of n, polynomial. Okay, so imagine you have an algorithm that takes a polynomial amount of time for a multi-tape Turing machine. Well, then it will take p of n squared. Now, here's the thing. Take a polynomial, square it, you get poly squared is equal to a poly. Another poly, but it's still a polynomial. Polynomial times a polynomial is a polynomial, no problem. However, take another polynomial, take a 2 to the poly, take a polynomial, raise 2 to that polynomial. Guess what? That's exponential growth. That's not a polynomial, not poly. That is not a polynomial. Okay? So, we have this difference between a multi-tape Turing machine, which takes a polynomial to a polynomial, so it's still polynomial, but non-determinism to determinism, that doesn't do that. A polynomial non-deterministic thing cannot be changed into a deterministic and remain polynomial. Can't work like that. Okay, so there's a major difference between that. Great. So that's really the end of section 7.1. Let me just... Okay. And now we're going to talk about section 7.2. Okay. And it's called the class P. Okay. And I said it last time, but let's rewrite it again. P is equal to the union, K is greater than or equal to 0, of time n to the K. Okay? That means all problems, languages, which can be answered in a polynomial amount of time. Okay? Now, some examples. We need some examples. Okay? So I'd like to give you some examples. Let me give you one quick example, very, very quick. Hold on, don't move. No, hold on, don't move. Ready? I'd like to give you some examples of polynomial algorithms. Ready? Every single algorithm in this 1,200-page book is a polynomial algorithm. Okay, so those are all polynomial algorithms. In fact, just to be more interesting, not only is it a polynomial algorithm, there's no algorithm here that's more than n to the 5th, probably. I mean, matrix multiplication is n to the 3rd. That's like an upper bound. But there's really nothing larger than n to the 5th, maybe n to the 6th or something like that. Okay, so all those are the polynomial algorithm. Let me tell you another problem which is polynomial algorithm. It's called the path problem. This is done in the book. I'm not going to go through it, but it's basically as follows. Given a graph and 2 points, S and T, so we're encoding a graph and 2 points on the graph. A starting point and an ending point. Question, is there a path from S to T in this graph? In other words, here's a graph with points and nodes and etc., etc. I don't know if it's directed or undirected. You'll have to look up in the book. Maybe it's directed. And here's one point S and here's another point T. There's a path from S to T. But let's say the graph has 100 nodes. It would be hard to see if they are connected or not. Anyways, path is a problem, and it's in P. Okay? Okay, why? Let me just tell you what the algorithm does. You can read the algorithm on your own, but basically, you start at the starting point and do a breadth-first search of that graph. And if at any point you get to the terminal point, the T, then you know you did it. And if you don't, you don't. But that breadth first search of a graph is a polynomial algorithm. Okay? Let me tell you another thing. The book does it. Okay? Rel prime. Okay? So given two numbers, m and n, tell if they're relatively prime. I got to tell you what that relatively prime means. It means, okay, if the greatest common divisor of m and n is 1. Okay, let me tell it to you another way. Another way is m can be factored into a product of a bunch of primes. N could be product into a bunch of primes. If they don't have any prime in common, then they're called relatively prime. Okay? And it's very simple, not simple, it's a very simple algorithm in order to determine the GCD of two elements. Okay? This algorithm is called Euclid's algorithm. Okay? And you can actually read it. It's not hard, but the point is, it's some mathematical algorithm. Basically, you take m and subtract n, and it's a recursive algorithm, and you determine what the GCD of it is. If the GCD is 1, then you say yes, they are relatively prime. Otherwise, you say no. Okay. The algorithm is about 3,000 years old. It's a lot longer than Euclid, but it's done. Okay, great. So this algorithm is done in the book. This algorithm is done in the book. Okay, there's another algorithm done in the book. It goes as follows. Every context-free grammar, telling whether or not something is in the context-free grammar or not, can be done in O of n to the third. Okay. We're not responsible for that. The book does it, but you're not responsible for that, and you can skip it. It does it with something called a dynamical programming, which is something that should be taught in analysis of algorithms. But anyways, we're not doing that, and we're not interested in it. I want to just tell you something else. About 20 years ago, somebody finally came up with a proof, and the title of the paper was as follows. 3 people in India came up with this paper, and the title of the paper was Fact. Prime is in P. In other words, you give me a number, and I'll tell you if it's a prime number in a polynomial amount of time. Okay? It was a little bit of an exciting result. People were very shocked by it. They didn't think that it could be done. But the algorithm was a fairly fancy algorithm. It's done in it's described a little bit in Corman, Lysason, and Revest. Okay, but those are three examples. But again, every one of these algorithms are in P, technically. In other words, they can be done in a normal amount of time. Okay, great. So you're going to read that section 7.2 on your own. Okay, great. Now, section 7.3. The class NP. Not P, but NP. So let me tell you what NP is. Not it takes a polynomial amount of time, but it takes a non-deterministic machine to do it in a polynomial amount of time. Now what we saw is polynomial computers are a lot faster than, not deterministic machines, deterministic Turing machines are a lot slower than non-deterministic machines. Non-deterministic Turing machines are faster than deterministic machines. Okay? And you cannot simulate a polynomial non-deterministic machine in a polynomial amount of time. So let's go through this. N time of n to the k is those problems that can be solved with a non-deterministic Turing machine in n to the k time. Now take the union of all n to the k. and you're going to get NP. Okay? Okay. Okay, so let's go through some thoughts. Time of f of n, okay, those things that can be solved in f of n time is a subset of those things that can be solved in let's see why this is true. These are things that can be solved by a non-deterministic machine in f of n time. These are things that can be solved with a deterministic machine. Deterministic machines are subsets, are special types of non-deterministic machines. Non-deterministic machines can go to more than one place at one time. Deterministic machines are special ones which can only go to one place at one time. So, this, by the way, if I was up to me, I would call this D time. Deterministic time, non-deterministic time. Okay? Unfortunately, the book doesn't do that, but that's fine. But you can keep it in your mind. You should call this deterministic time and non-deterministic time. Let's go through this. You ready? These are problems that can be solved with a non-deterministic machine in f of n time. These are problems that can be solved with a deterministic machine in f of n time. Deterministic machines are special types of non-deterministic machines. So if a deterministic machine can solve it in f of n time, then a non-deterministic machine can also for sure solve it in f of n time. That explains that. Now, next, what was that result I just showed you about how we can have a deterministic machine simulate a non-deterministic machine? Well, what that says is as follows. Okay. It says, you give me a problem which takes a non-deterministic Turing machine f of n time to solve, and I will find you a deterministic Turing machine which can solve it in 2 to the f of n. Maybe there should be an O of f of n time or something like that. But let's leave it like that. Again, you give me a problem that can be solved with a non-deterministic Turing machine in f of n time, then that simulation shows that there's a deterministic Turing machine which could solve that same problem in 2 to the O of f of n. Okay? Okay, great. Okay, great. Just want to give you a name for this. NP does not, many people think that NP stands for not polynomial. P stands for polynomial, NP stands for not polynomial. It doesn't. It stands for non-deterministic. Deterministic polynomial. Okay? Okay, great. Before I go on, I just want to tell you the way the book describes it. So I'm slightly different than the book. I'd like to present the book. The book doesn't want to talk about non-determinism as doing more than one thing at one time, although it's equivalent. So the book talks about something else. Okay? Polynomial verifier. Okay. And the idea is as follows. You ready? Let's talk about tests. Let's talk about tests. Okay? You take a test, it takes a certain amount of time. Question, how much time does it take to check if a test is right or wrong? So you're a student, you don't know this, I'm a teacher. So the answer is, it's a lot shorter to test, to check a test. It takes a lot shorter to mark a test than actually take a test. Okay? Now, as you go on in life, you get bigger and bigger tests. So, your SAT, your Regents exams were big, but then the SAT was bigger, and then you graduate to college and you go to graduate school, you take a bigger test. And let's say you wanted to become a lawyer, God forbid. You would have to take a bar exam, which is like a 3-day exam. So, the point is, as hard as tests are, you could talk about marking a test. And marking a test takes shorter than taking a test. So taking the bar exam takes 3 days. Marking the bar exam probably takes 3 hours or something to do like that. Okay? So we could talk about verifiers. Okay? A verifier is as follows. A problem has a polynomial verifier. Problem A has a polynomial verifier, means that if you gave it an input, you can give a computer an input, that means a potential problem, and a certificate. In other words, we're looking for a solution. So in prime, we're looking for what are the factors, yes or no. For what we just talked about, path, give me a path, a potential solution. So a certificate is a potential solution. So this is a problem. This is an input to a problem. This is a potential solution to this problem. Okay? Now, the idea is as follows. Usually, NP problems are harder than polynomial problems. Okay? But the way they define NP problems are problems that if you give it an input and you give it a potential solution, the computer can verify that this is an answer to this question in a polynomial amount of time. In other words, I don't want you to be able to solve it. This is old deterministic. I don't want you to be able to solve it in a polynomial amount of time. I want you to be able to tell that a given solution is a solution. Okay? And if a problem is that, then we call it NP. Okay, so let's go. Let's review. To me, an NP problem is a problem that a non-deterministic Turing machine can solve in a polynomial amount of time. The book accepts that definition, but they also give another definition. The other definition is NP are those problems which a deterministic Turing machine can Turing machine can tell yes or no if a potential solution is in fact a solution within a polynomial amount of time. The book's doing this is because we don't like non-determinism. It's a strange concept. It doesn't exist in the world. None of our machines are non-deterministic. All our machines are deterministic. You do one thing, then you do another thing, then you do another thing. One thing at a time. So Mr. Simpson doesn't want to use this concept of non-deterministic Turing machine. I don't know what he wants to use, whatever, but this is another definition, polynomial verifier. It's more formal, it's more exact, other people do it too, and again, it doesn't use this concept of a Turing machine doing more than one thing at one time. That's a not natural thing to talk about. So instead of talking about solving problems with a deterministic machine in a polynomial time, we talk about verifying problems with a deterministic machine in a polynomial amount of time. That's exactly what this is all about. Okay? Turns out that those two solutions are exactly the same. Those two definitions are exactly the same, and that's very nice. Okay? But we're gonna stick to our thing about non-deterministic machines, and we're going to do it nicely. Great. So now I have to give you some problems. Basically, the rest of the semester is talking about the rest of this section 7.3 is talking about NP, some problems in there, and then section 7.4 is called NP completeness. We'll talk about that. So I have to talk about NP. Okay, so we're talking about NP, so we need a lot of examples of NP problems. So I'd like to show you some of them. Okay? One is called the clique problem. Let me tell you what a clique is. A clique, it's like in a class. You have a clique, an elementary school class. A clique is a group of little kids where everyone is friendly with where everyone is friendly with each other. Okay, they're all part of one gang. Okay, let's put it in terms of a graph. A clique is a subgraph where every node is connected to every other node of the subgraph. Okay? So let me give you an example. Here is a triangle. So a triangle is 3 nodes where every single thing is connected to every other thing. Okay? 1, 2, 3. Okay? Question. Does this graph have a clique of size 4? Okay? Now if you may say, okay, here's 4. 1, 2, 3, 4. No, that doesn't work because this guy is not connected to this guy and this guy is not connected to this guy. So this is not a clique of size 4. This is just a square. Okay? As opposed to this, here is a clique of size 4. 1, 2, 3, 4. Every single thing is connected to every other thing. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Every single node is connected to every other node. So this is a clique of size 4. Question, does this graph have a clique of size 5? Okay? And if you stare at it for a long enough time, you'll see it does not have a clique of size 5. Okay? So now we describe the language of a clique, of the clique problem. It goes as follows. CLIQUE is equal to the encoding of a graph and a number k such that G, the graph, is an undirected graph with a clique of size k. Okay, so that's what this language is. Okay, and basically what happens is you put an encoding. You have a Turing machine. You put a graph on it. You have a k. K is some integer. You have the encoding of the graph on the Turing machine tape. You go back and forth trying to find, is there a graph, is there a thing of length k, yes or no? Okay, great. Okay. By the way, how does a Turing machine do this? Okay. Well, it's a non-deterministic Turing machine, so let's just say how it would do it in a non-deterministic Turing machine. Let's say the graph is of size n. So, how do we solve this problem? Non-deterministically? Very simple. There are n nodes in this graph. Non-deterministically, try all n to the k. Now that's exponential amount of nodes. Non-deterministically, try all of them, and go through for each one of them, see if every single node of those k things are connected to every single other one. Okay? Let's talk about it in terms of verifier. If I give you a graph and I ask you, is there a 4, and I give you this thing, these 4, 1, 2, 3, 4, you can verify, you can see they're connected to each other, and therefore they do form a clique. Okay? So the clique problem is a thing, and we could say as follows. We could say for this graph H, we have H, comma 4 is a member of clique. In contrast, H, comma 5 is not a member of clique. Okay? One is a member, one is not. Okay? Okay, great. So this is one example of an NP problem. We're going to see a lot of other examples of NP problems also. Okay, let's do another one. Another one is ham path. Ham path. Let me tell you what that's about. Given a graph. Okay, I'm going to do it with an undirected graph. I'm going to do it with an undirected graph because it makes things a little bit simpler. Question. Is there a way, without lifting your pencil, of starting someplace, going through the outer graph, finishing, it doesn't have to finish in the same place, but hitting every vertex? Is there some path that hits every vertex? Let's see. Start here, go around here, finish there. Yeah, this one does. Right? Start here, go around here. You don't have to hit every edge, you have to hit so the answer is yes here. Let's make it a little bit more complicated. Okay, how about here? We'll put in extra nodes. Go around here, go here. Oh, you have to hit every node exactly once. You can't hit any node more than once. So let's do this. Maybe, no. No. Okay, the answer is no over here. There's no way you can, maybe we can start here. Oh, this, we can do it. Let's do it. One. Okay, let's go through that again. Start there, go there, go there, go around here, go around here. Stop there. I hit every single node without picking up my pencil. So the answer is yes over here too. Okay. How about here? Okay. And the answer is yes over here too. Watch. Here, go around here, finish there. The answer is yes over here. Let's make it a little bit more complicated. 1, 2. Okay, the answer is no over here. There's no way you're going to start, and because you can't go from anything to any other thing without going through that. So you do that once, but you're finished. Okay, so ham path is, as a language, it's equal to the encoding of graphs such that G is a graph with where one can have a Hamiltonian path. And again, what's a Hamiltonian path? It's a graph. It's a path that starts someplace, finishes someplace else, and hits every single vertex exactly once. Okay? So this is another way. By the way, how does one do it? You have to try all n factorial possible paths. Okay? There are n. You have n vertices, so you have n factorial possible complete things, and you have to see for each one of them. You non-deterministically check for each one of them. See if you can go from every node to every other node. Okay. So let me say that a little bit more clearly. look at all n factorial permutations of vertices, okay, and see if any of them hit every single, there's an edge between each and every one of them. So you're going to have x1, that's one vertex, x2, that's another vertex, x3, another vertex, xn. See that there's an edge from here to here, an edge from here to here, an edge from there to there, an edge from there to there. Make sure there's complete edges. That means there's a path between each one of them. Okay? And that means that there is a Hamiltonian path. That is, going through all these can be done in a polynomial time if you have non-determinism. Okay, two more examples. We'll see some more examples even later. Two more examples that are very important. One is called the subset sum problem. Okay, let me just tell you what it is, and then I'll write it up. You have a bunch of things. Everything has a size. Okay, think about it. You're going to the country. You have a car. You want to take a bunch of things to the country, but you have a car, and your car has a finite capacity. Okay, question, is there a subset of your things that can equal exactly your capacity? Okay, it's a yes-no question. Okay, let me give it another way. Okay, you have a bunch of numbers, 5, 18, 23, 16, 25, 17, 18, we did 18 already, let's do 19, 3. Okay, there's a bunch of numbers, and you want t. T is another number. You'll say maybe it could be one of these numbers. No, actually it wouldn't be interesting. Let's say 52. Question, is there a subset of these numbers that's exactly equal to 52? And 25 plus, let's see, 23 plus 5 is 53. That doesn't work. 19 plus 8 is 17. Yeah, we got it. 25 plus 3 is 20, and 19 is 22, plus 5 is 52. I think that's 52. 25 is 30, 50, that's 49 plus 3 is 52. So yes, there is a subset here that's equal to this. What's the subset? This, 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 and this. Okay? Okay, great. Let's be a little bit formal about it. Subset sum. Okay, so you want to find a subset where the sum is equal to something. So it's equal to an encoding of S comma T such that S is equal to x1, x2, xk, k numbers, and there exists a subset y1, comma y2, comma yl, subset of x1, x2, xk, such that Okay? There's a subset of these numbers such that the sum of I equal 1 to L of yi, if you add up all the elements in the subset, it's equal to t. Okay? So again, what's the subset sum? It's encodings of numbers, sets of numbers, and a capacity such that there is a subset of the numbers such that when you add up all the numbers in the subset, you will get exactly equal to t, the capacity. Okay? How would you solve this? Very simple. You give me n numbers here. There are 2 to the n subsets. I have to try all 2 to the n subsets. Okay? And if any of those, if I add up any of those subsets and it equals t, bingo, I'm accepted. Okay? Notice all the problems we have are either exponential or factorial. Okay? And that's pretty much true. And again, you can do a hard problem like this and search through all 2 to the n possibilities or all n factorial possibilities very easily with a non-deterministic Turing machine. You cannot do it, as far as I know, you cannot do it with a deterministic one, or you cannot do it easily with a deterministic one. Okay, great. Okay, great. Now, so we just had 4 examples of NP problems. Let's just go through them. The clique problem, the Hamiltonian path problem, the subset sum problem. Okay, sorry, 3 problems. We're going to see another one in a second. So we had 3 of these NP problems. Okay, so these are nice examples of NP problems. Let's just go through some theory. P is a subset of NP. Let's just see why that's true. Why is this true? What this says is these are all the problems that can be solved by a non-deterministic machine. These are in a polynomial amount of times. These are all the problems that can be solved in a polynomial amount of time with a deterministic machine. Okay? The reason for this is because time f of n is a subset of n time f of n. We saw this before. The problems that can be solved in a f of n time can definitely be with a deterministic machine can definitely be solved with a non-deterministic machine in f of n time for a very simple reason. Because deterministic Turing machines are a special type of non-deterministic Turing machine. So if you can solve a problem with a deterministic machine in f of n time, then you can definitely solve it in non-deterministic. Now here we're not talking about f of n, we're talking about p of n, polynomials. Now let's restate. If you can solve a problem with a deterministic Turing machine in a polynomial amount of time, then you can definitely solve it with a non-deterministic Turing machine in polynomial amount of time. Okay, the same polynomial. Why? Because deterministic Turing machines are a special type of non-deterministic Turing machines. So if you can solve it with a deterministic machine, that same deterministic machine is right in here also. Non-deterministic Turing machines are here's deterministic Turing machines. They are special types of non-deterministic Turing machines. Okay, let's put it another way. Okay, if you have a problem in here which can be solved in a polynomial amount of time by a deterministic Turing machine, then it can be solved by a non-deterministic Turing machine in the same polynomial amount of time. Okay, that's what that says. Very good. Let me say it more intuitionistically. Easy problems, and I told you before, all the problems in here are easy problems, can definitely be solved in a short amount of time. These problems can be solved in need of more time to solve. Okay, these need exponential or factorial amount of time to solve. These are more easier. So if you can solve a problem in a polynomial amount of time, you can definitely solve it in an exponential or factorial amount of time. Okay. The big question is the other way around. This is a question mark. Let's see what it means. It means, question, can these hard problems, are there any tricks to solve these problems in a short amount of time? Okay? And there are two possible answers for this question. One is P equals NP. In other words, if P is a subset of NP and NP is a subset of P, then they're equal. Okay? And the other possible solution is, here's NP, here's P. They're not. Now, most people think that this seems a little bit more likely. There are easy problems and there are harder problems. This seems less likely, and I'd like to explain to you why. Because if there are tricks to solve these hard problems, how come we didn't find these tricks yet? Okay, well, you might say, we didn't look long enough. It takes a long time to find tricks. Okay, but these problems have been around for 50 years and we still haven't found a good trick. Most people think that there doesn't exist good tricks, and this is the way to look at it. Okay, great. Okay. We're going to spend the next section talking about these things and going through them very carefully. I just want to say this is the famous P equals NP problem. It's a question. Again, most people think that this is the correct answer, but it's hard to prove it. Okay? And we'll talk more about it at the end of next section. Let's do it. Section 7.4, NP completeness. Okay. And what these are problems that are NP, like we saw before, and we saw 3 examples of them, but they're in some sense the hardest NP problem. They are the hardest NP problems, and we'll see we do not have polynomial algorithms for them. That doesn't mean they don't exist, but we don't. And I have to explain to you what I mean by the hardest NP problems. Okay, so let's do that. Okay, so first I have to tell you about another problem called SAT. Okay, and SAT stands for satisfiability. Satisfiability is a logic problem. Okay, and it goes as follows. Here's a typical logical formula. X or Y and Z arrow not X and X and Y bar. Okay, question. This means and, this means or, this means implies. Can you make this a true statement? And the answer is yes, you can. If you said X is equal to true, that makes this true. That makes this true. Okay. What about Z? So I gotta make this true. So I said Z, if X is equal to true, X bar is false, so I better make sure that Z is false. Okay? What about Y? I don't care what Y is. Y is either true or false, so this thing is still true. So yes, this statement is satisfiable. Okay? Okay. I'd like to show you another statement. Let's try this. X and X bar or Y and Y bar or Z and Z bar or W and W bar. Okay, this has 1 variable, 2 variables, 3 variables, 4 variables. Question, is this satisfiable? Can I in some way make this statement to be a true statement? Okay, I'd like to rewrite this statement so you could see it a little bit more clearly. It says as follows: x and x arrow y and y arrow z and z arrow w and not w. Okay. Now let's see how we can do this. Let's say x is true. That means if this is also true, again, in order for this statement to be true, every single one of them is true. So this has to be true and this has to be true. Now if these two statements are true, if x is true and x implies y is true, that means y is true. Now if y is true and y implies z is true, that means z is true. If z is true and z implies w is true, this is modus ponens, then w is true and w is false. No way in the world you can make this true. No way. You can make a truth table as long as you want, fill in every single thing here. You'll see that this doesn't have a t on the final thing. In other words, if you were made a truth table of this statement, it would all be f's. Contradiction. It would all be f's. Okay, so this is called the chain rule. Okay, great. Okay, now let's make this a formal statement. So this is equal to the encoding of a logical statement such that phi is a satisfiable logical formula. Okay, so let's go through this. Some logical formulas will be satisfiable. You will be able to do it. You will be able to make them true. Some will not. Okay, question. How do you do this? How do you write a program to do this? Well, very simple. Take the logical formula, make a truth table out of it. Okay? We learned how to do truth tables. We know how to do truth tables. So we can make a computer go through a truth table. Now, what do you have to do with the truth table? You have to fill out all the rows of the truth table. Okay? And as soon as you see a T as your final answer in the truth table, okay, in that final column of your truth table, if you see a T, you stop, you say, this is satisfiable. If you don't, if you see F, 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 you have to go on and go on and go on until your truth table's finished. Question, how big is your truth table? Answer, it depends how many variables you have in your formula. This had 1, 2, 3, I erased the last one. This had 4 variables. Your truth table will be 16 columns, rows long. Okay, the one before had 3 variables. 3 variables will have 8 columns long. Okay, if you have a formula with n different variables, you're going to have 2 to the n rows in your truth table. 2 to the n rows in your truth table. So you have to go through, potentially have to go through all the rows. Let's just go through what that says. You have to go through the rows. If the final answer in any one of your rows is a T, then it's satisfiable. You can satisfy that formula. You can make that formula true. Otherwise, if they're all F's, it's unsatisfiable and it's not in your language. Okay? Problem is, 2 to the n is a very long time. If n is equal to 100, okay, then 2 to the n for a normal computer is 2 to the 100, and it would take, I did this before in the beginning of this chapter, 401 trillion centuries to solve. Can't be done in a normal amount of time. So this is a very hard problem. Okay, we had other problems as 2 to the n. N factorial is even harder than that, but these are very, very hard problems. Okay? Okay? How do you do it with a non-deterministic Turing machine? Very simple. You ready? You non-deterministically branch out to all 2 to the n possibilities at the same time. Okay? Branch out, try x is true, x is false, y is true, y is false. Non-deterministically try that. Okay? And for each one of them, do the truth table for that particular choice of values for your formula. And if the final result is true, you say true. Otherwise, you say false. Okay? Conclusion, SAT is a member of NP. It's an NP problem. Okay? It is not well, as far as I know, it's not polynomial, because I don't know how to make a truth table come out in a polynomial amount of time. Okay, great. Now we go for a little theory. Okay, so we have another example and another example and another example. We had 4 examples of NP problems, and there are many, many, many others. Okay. Now we have to do a little theory before we go further. A second. This is a book from 1979, I believe. It's called Computers and Intractability, A Guide to the Theory of NP Completeness. In the back of this book, there's an appendix with hundreds of NP complete problems. Hundreds. Okay, and that's a 40-year-old book. There are thousands and thousands of NP complete problems. Okay, let's go further. Definition. So we have to do a little bit about theory. What we're trying to motivate here is we're trying to show how does one compare 2 problems. Okay, how do we say one problem is harder than another problem? That's what we're aiming for. Definition. A function f from sigma star to sigma star is a polynomial time computable function. A function f from a is a polynomial time computable function if some polynomial time Turing machine exists that computes f. Okay? In other words, if you put on your Turing machine some word, okay, then you can get a polynomial algorithm to output f of w. Okay? So that works very well. Okay? So a function is polynomial time computable if there's a Turing machine that can actually change from the input to the output, okay, in polynomial time. Great. Now, this is probably the most important definition in this section, well, in this chapter. So let's do it carefully. Definition. Language A is polynomial time mapping reducible, polytime mapping reducible to language B. Okay, we write that as follows: A less than or equal to, with a little p on the bottom that stands for polynomial, B, if there exists f from sigma star. That means it accepts a word and it outputs a word such that W member of A, if and only if F of W member of B. Okay, we're going to spend a lot of time explaining what this definition means. But basically, what this is describing is a relationship between language A and language B. Now, before we talk about languages, let's just remember what we're talking about. We're talking about problems, okay? But in Sips's book, a problem is a language, and you either accept a word or don't accept a word. The input is either part of the language or not part of the language. So you have to get this connection between languages and problems down pat. You have to get that into your head. So when I say language A, I'm also talking about problem A. When I say language B, I'm talking about problem B also. Okay? And again, a language is a subset of words. The problem is, if I input this word, should I accept it, yes or no? Okay? Now we have to make a picture of what this looks like. And the picture is a very nice picture. So you have what's called a B decider. Okay? That's a language B. You have a language B decider. Okay? Now let's just think what a decider is. A decider is a machine, Turing machine, that a word goes into it, okay, and output, yes, the word is in the language, or no, the word is not in the language. We saw this in the beginning in chapter 4, but here we're having yes, no. We're always talking about deciding. We don't go into infinite loops here. Okay, so this is a language B decider. So again, language B is a subset of words. Okay, you input the words into this Turing machine, and it's going to tell you this word, yes, it's in, or no, it's not in. Okay, great. Now that's a B decider. What we're doing here is we're making an A decider. Let me show you how it goes. Okay, what we do is hold on, sorry. You have a word coming in here. You have a, I'm going to call this a polynomial transformer. That's exactly what we did here. Polynomial time computable function. Okay, look what happens. The word comes in here. This function f takes words over here and outputs words over here. And then we want the following thing. This word is accepted into A if and only if f of w is accepted into that. In other words, if the answer is yes here, then we want the answer to be yes over there. Now this whole machine which accepts a word to be thought of as an input to A, changes the word into an input of size B, checks the B decider. This whole machine is called an A decider. Okay? And this line says that the output to this machine should be the same as the output to this machine. In other words, the word is accepted into the language A. The word is an input into A. It's in the language, if and only if FW, if we change the word, we get it like that. Now, let's go further. Let's say this is polynomial. This we know is polynomial because we're only talking about polynomial time computers. These transformers are known polynomial. Well, a polynomial plus a polynomial, then this whole thing is a polynomial. This whole computer is a polynomial plus a polynomial. You can do it in polynomial. Everything is deterministic here. Okay, so here's the point. If B has a polynomial algorithm, then A, this is assumed to be polynomial. So let's go through that. If B has a polynomial algorithm, this we assume to have a polynomial algorithm. If this has a polynomial algorithm, then A has a polynomial algorithm. Let's state that again. If you can solve B, you can definitely solve A. Okay. Conclusion, B is harder or equal to A. Key point. B is harder because if you can solve this one, you can definitely solve this one. Think about walking up flights of steps. If you can walk up to the fourth flight of steps without huffing and puffing, you can definitely walk up to the third flight of steps. In other words, if you can solve the walking up to the fourth floor problem, you can definitely solve the walking up to the third floor problem. Okay? And that's exactly what this is all about. Okay? So what we just did now was we made a relationship between two problems. We said when one problem is hard or harder or as equal to another problem. And the idea is if you can change the input of one problem into another problem and then solve the other problem, then this problem is hard or equal to this problem. Okay, you write it like this. A less than, A is less hard than B, less than or equal to B. Okay, that's going to be very important. But let's do one other thing. Let's say there is no polynomial algorithm for A. There is absolutely no polynomial way of solving this in A. Well, what can you learn from that? Well, this is polynomial. You assume this is polynomial right here. And if this had a polynomial algorithm, then you would be able to solve this in polynomial time. Just follow this by this. Since this does not have a polynomial algorithm, that means this does not have a polynomial algorithm. Let's say it in terms of this. If this is so hard that there's no polynomial algorithm, then this problem, which is even harder, for sure doesn't have a polynomial algorithm. There's no simple way of doing it. Good. Another definition. Definition. A language B is NP complete. Okay, that's what this section is called, NP complete problems. Okay, it's NP complete. Complete means the hardest. If one, B is NP, it's in NP. In other words, it's a hard problem. It's an NP. And two, every language A in NP is polytime reducible to B. What does that mean? Every language A in NP can be changed into B. Okay? What this means is, i.e., B is harder or as hard as, I'm sorry, let's use the word or equal, to every other problem in NP. Okay, so I'd like to make a picture of this. And the idea is as follows. Here's your NP. Here's your problem B. This problem, A, can be changed into B. This problem, A prime, can be changed into B. This problem, D, can be changed into D. This problem, C, can be changed into D. Every NP problem can be changed into B, which means B is harder than this, 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 B is harder than every single problem. Okay? I'd like to draw it another way. Here's your P. P is a subset of NP, we all agree on that. Here's your problem B, it's in NP. Okay? And every single problem is harder. So the way to think of this is, in some sense, this is easy, harder, 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 and these NP complete problems are the hardest. So I'd like to think of them as the hardest problems. Okay? I'm going to put them, these are the hard problems. Okay, out here are the hard problems, the NP complete problems. Okay? Okay. I want to keep this theorem because this is this is an important theorem. I'm sorry, I want to keep this definition. I want to keep this picture. Every language in AB is polynomial time reducible to B. Okay. By the way, I don't have an example yet of what an NP complete problem is. I gave you 4 examples of what NP problems are, but I don't have an example of NP. Let me just tell you why it's so hard to give you such a thing. Because look what I would have to do. I have to show, well, I have a lot of problems in NP, but I have to show that every other problem can be reduced to it. I showed you, we did 4 examples, but I showed you there's hundreds of other problems that are in NP. How do I show that every single one of them changes into B? We'll see that in a second. Okay? So that's why it's hard to give a definition. Okay. Let's give a theorem. If A is less than or equal to B. In other words, A can be changed into B. In other words, A is easier or equal to B. And B is in P. That's in here. Then A is in P. Okay? Now, I already said this already, and here's the way to do it. Here's the picture. Here's a B decider, here's a yes, here's a no. Change the whole thing. This is an A decider. Let's just see what this is saying. Okay, this is saying exactly what I said before. If this means that A is reducible to B, and B is in P, if there's a polynomial algorithm to do this, then guess what? You follow this polynomial plus this polynomial, you can solve the A problem. Then A is in P. It's just equal to, it can be solved by following this followed by that. Very simple. Okay. Okay, great. But there's another theorem too, and we're going to get to it in a second, but I just want to show you something. Let's say there's another problem there's a problem B, and there's a problem, let's say C, well, let's call it B prime, okay? And you can change B into B prime. And let's just see what this means. It means every single problem, including polynomial problems, every single problem can be changed into B. And then B can be changed into B prime. What else do you know here? Well, B is NP complete, because every problem can be changed into B. But if you can change B into B prime, then B prime is also NP complete. Let's see why that's true. Okay, we could do it right here. If you can change every problem A into B, and then B can be changed into a B prime problem, then guess what? A can also be changed into a B prime problem. B prime problem. Again, if A can be changed into a B problem and B can be changed into a B prime problem, then A can be changed into a B prime problem. Okay. Okay, great. Okay. So what I'd like to do is, once you have an what I like to do, what we're doing for, what we're aiming for is, once you have an NP complete problem, it's very easy to show that another problem is NP complete. Hard problem is to show the first one, but once you have one that's NP complete, all you have to do is convert one to the other. Bingo, everything is NP complete. Okay, so let's do a conversion. We haven't done a conversion from one problem to another. We've given the theory of it, but we haven't actually done it. So let's find a nice simple problem and convert one problem into the other. Okay, so a special type of Boolean formula. It's called 3CNF. 3CNF. Okay? It's the CNF stands for conjunctive normal form. Okay? Conjunctive means conjunction means and. Okay, so let me just show you. Here's a typical 3CNF formula. X or Y bar or A and X bar or B or C bar and Y or B bar or A bar and B or A bar or X. Okay? Now, this is called a 3CNF formula. Why? Because each clause has three elements, X, Y bar, A, da, 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 da. Each one has three elements, and inside you only have ors, nots and ors, nots and ors, nots and ors, etc. And outside's conjunction, ands, and. Okay? So this is a logical formula, and you can ask this question, is this satisfiable or not? Okay, but more important than that, we're not going to go through this exactly, but we're going to just state it. You ready? Every logical formula can be put into 3CNF form. Okay. We had something like that similar when we talked about Chomsky normal form. You said we had a context-free grammar, we changed it into a Chomsky normal form. Well, it turns out that every single logical formula can be put into this 3CNF formula. Okay? And it's a nice little thing. We're not going to do it right now, but it's in the book, and it's very easy, and it's not hard. Okay, great. Okay. Let's erase this. Okay, so we need to have an example of changing one language into another language. Okay, so 3CNF, also called 3SAT, is polynomial time reducible to click. Let's just remember, click was our problem about graphs and a number. Tell me if it has a click. And 3SAT or 3CNF, that is where I give it a formula in 3CNF form and tell yes it's satisfiable or no it's not satisfiable. Okay? Okay. So basically what I'm going to do is as follows. We're going to have a we're going to have a click decider, which is going to come out a yes or no answer. We're going to have a machine that goes in here, a word. Okay, I'm sorry. We'll copy that in a second. Okay, and basically what I have to do, this whole thing is going to be a 3CNF decider. Okay, and basically a logical 3CNF formula is going to come in here. It's going to change to a graph and a number, and we're going to get a yes-no answer out of here, and we're going to get a yes-no answer out of here. Okay? That's what we have to do. And once we do this, then we prove that it's logical like that. Okay, let's just see this. Let's just state it more clearly. Phi is satisfiable if and only if f of phi has a click. Okay, I'm going to say how big the click is. Number of clauses in phi. Number of those three-pronged things. Okay, each one of those is called a clause, a part of the formula. 3 and 3 and 3 and 3. Number of clauses, that's how big the click is. You'll understand it in a second. Okay, so, I'm going to erase this. The hard part is drawing that. We're going to draw that. We're going to give the machine, this F machine, this is a polynomial machine that's going to take a logical formula and turn it into a graph. I just want to say this is a fascinating thing in itself because look what you're doing. You have a logic problem and you're changing it into a graph problem. That's interesting. This shows how these things are all interconnected. Okay. Okay, so I just want to go through that formula again. Okay, here's a typical CNF formula: X or Y bar or A, and X bar or B or C bar, and Y or B bar or A bar. Remember, bar means not. Okay, and B or A bar or X. That's a nice little formula. And I'd like to convert that into a graph. Okay, so let's convert it into a graph. Okay, I got to give you the nodes and the edges. So here's the node. It's not hard. There are 4 clauses here. 1, 2, 3, 4. I'm going to have 4 sets of nodes. It's going to be like this: X, Y bar, A, X bar, B, C bar. Okay, here we have YB A bar, YB bar A bar. y, b bar, a bar. And finally, this is b a bar x. B a bar and x. Okay. Here are the clauses. Here are the clauses. Okay. Now, I'm sorry. Here's the nodes of the graph. And let me tell you what the graph is. It's very simple. Ready? There's an edge from one node to another node if they get along. In other words, if they don't contradict each other. So let's go through it. X has no problem with B. X has no problem with A bar. X has no problem with X. X has no problem with Y. X has no problem with B bar. X has no problem with A bar. This is pretty good. X has no problem with C bar. X has no problem with B. X does have a problem with X bar. So there's no edge from here to here. And that's an important thing. There's no edge from here to here. Okay? Fine. Now, the idea is as follows. If I'm going to make one of these true in here, let's say I have to make this clause true, and this clause true, and this clause true, and this clause true. If I'm going to make this clause true, let's say there's three ways of making it true. I can make this true, I can make this true, or I can make this true. Or. Okay? Well, if I make this true, then what can I make true over here, and what can I make true over here, and what can I make true over here? So if I make x true, I can do everything else over here. Here's x is true, but I can't make x true over here. Okay, good. Okay, let's do with y. You ready? Y has no problem with B. Y has no problem. Y bar has no problem with B. Y has no problem with that. Y has a problem with Y bar has a problem with Y. So we can't make a line like that. However, Y bar has no problem with B. Y bar has no problem with A. Y bar has no problem with C, with B, or with X bar. Okay, great. Let's do with A. A has no problem with B. A does have a problem with A bar. That's not good. So we're not going to put a line there, but we are going to put a line here. Okay, and A corresponds to that, and A is going to correspond to B. A and A bar, buzz, no good. Notice, by the way, that A bar does get along with A bar. That's not a problem. Okay, etc., etc. Okay, each one. X bar, we dealt with this. X, no problem with that. Okay, now you got to fill in all of them. Okay, let's just do C bar. C bar gets along with everybody here, here, and here. So C bar gets along with everybody. Okay, great. Now, question: Is this formula satisfiable? And the answer is yes, it is satisfiable. Let's just do an easy way of making it satisfied. Okay, I can choose this to be satisfied. Okay, X is satisfied, which by the way takes care of this one. So that takes care of that. That's no problem. Okay, now I can't, if X is satisfied here, I can't do X bar here. So it must be either this guy or this guy. Now if I choose B to be satisfied, that's fine, but then I can't be B prime to be satisfied. So I can choose Y, or I can choose A bar. Which one do you want to choose? Let's try A bar, just to be more interesting. Okay, so if I make this true, I make this true, I make this true, and I make this true. By the way, B is satisfied here too. Okay, well what will that correspond to? Well, it'll correspond to this. Okay, it'll correspond to a click of size 4 between them. Let's do it. You ready? Let's do it. Okay. Okay, so let's do this. And watch this. There is a edge from here to here. Okay. There's an edge from x to a bar, because there's no problem with x to a bar over there. By the way, there's an edge from b to a bar. They have no problem getting along with each other. Okay, and now we have to worry about this guy. There's an x from x to x. That's for sure getting along with each other. Okay, and what else? By the way, x gets along with a bar also. Okay. What else? Well, b gets along with x bar, that's for sure. Okay. And there we have a 4 clique. We have a clique of size 4. 1, 2, 3, 4. Okay. So here's the thing. If this is satisfiable, this has a clique of size 4. If this is not satisfiable, it doesn't have a clique of size 4. Now, I'd like to do an example where it's not satisfiable, because this seems very easily satisfiable. So let's do a clique of not satisfiable. Hold on. First, we have to say hello to my beautiful daughter. Come here, beautiful daughter. Okay, hold on.
I want to go in the attic again.
Okay, tomorrow. Say hello to everybody. Who's a princess? Are you going to sleep now? You sleeping here or there? Okay, so let's do another example where this is not satisfiable, because it's much more interesting when it's not satisfiable. So we had a good example of a logical formula that's not satisfiable. Remember, x implies y, y implies z, z implies whatever, not, and then you have not w. Remember that? So let's do a version of that for the 3CNF. Okay, here's the version. You ready? Sorry. Here's a nice logical formula. And it goes as follows. X or X or X. That's basically X. Okay? And X bar or Y or Y. That's basically X implies Y. And, but it's in 3CNF formula. And Y bar or Z. That's basically Y implies Z. Okay? And finally, and Z bar or Z bar or Z bar. That's basically not Z. So let's go through this. X and X implies Y means Y is true. And Y implies Z means Z is true. And here we have Z is false. Great. Let's do a clique problem from this. So it's very simple. We're going to follow the same rule. X, X, X. This is going to be X bar, Y, Y. This is going to be Y bar, Z, and Z. That's that. And this is going to be Z bar, and Z bar. Okay? Okay, great. Let's see what gets along with what. X gets along with both of these Y's. All these X's get along with both of these Y's. Okay, but they don't get along with this one. Okay, great. These Y's, Z's get along with everything here. Ooh. Okay. X bar gets along with Y bar. Y gets along with Z. Y gets along with Z. This gets along with that. This gets along with that. This gets along with that. The only thing is Y doesn't get along with Y bar. Okay, I might have left something off. Okay, notice everything here gets along with everything here. Okay? Okay. And finally, Z bar doesn't get along. Anyways, here's the main point. You will not be able to form a 4-click out of this. Okay? And you can try to do it as much as you want. You can't. Let's just see what happens. If X is true here, you pick any one of these trues. You have to choose X to be true. You also have to choose Z's, so it could be any one of these. So these have to all be true, because you're going to choose one of them. They all say Z bar, so they're all true. So you're going to have to find a thing with one of these guys and one of these guys. Okay? But you're not going to be able to make a thing, because let's go through it. If X is true and X bar is false, you won't be able to try that, but you'll have to choose Y. So you'll have to have a Y in them. Very good. Now Y is going to be true. So let's just figure out. In your click, you could have one of these. You can have one of these. Okay? You're not going to have this, but you can have, you're going to have this. That's very good. Okay? And now, what else are you going to have? You're not going to have, if you're going to have Y to be true, then Y bar is not going to be true, so you're going to have Z. Z is going to be true. Okay? Z has to be true. Okay? Now, there's no way in the world, the only thing, the Z bars are not going to match up with the Z's, so the only thing that's going to be connecting here is this guy, these guys. They're all going to be connecting to here. That's the only thing they're going to be connecting to there. Okay? And the only thing connecting from here, ooh. Okay? These guys are not connecting to here. So it's, we have all the things that could make into our thing, but they're not connecting. They're not connecting. So these three guys, by the way, they connect very nicely to all three of these guys. These get along very well. But the Y here is only going to connect to here, and this guy is not going to connect to any of them. So you can't do it. Okay? The only way you're going to have any of these guys is choose one of these guys. It's going to connect to this. Very good. This guy is only going to connect to this. Okay? And this guy is not going to connect to this. Conclusion, there is no four click in this thing. Okay? Great. Okay. Conclusion. Click is harder or just as hard as 3-SAT, or 3C and F. Great. 2 theorems. Theorem. If B is NP complete and B a member of P, then P equals NP. Let's just see what that is. If B is an NP complete problem, and B actually lies in P, in other words, if you find a trick for B, and you land it in P, in other words, you can find a polynomial algorithm, then P is equal to NP. Okay? Let's just show you what that means. Here's your P. If you have B, okay, and everything reduces to B, and it turns out that somebody comes up with a good polynomial algorithm for that. Well, that means that this guy is not here, but it's here. Okay. What that means is that every single problem reduces to something in P. If every single thing reduces to something in P, then all those problems can also be solved in P. Conclusion, this is the way it looks. NP is equal to P. All these problems can really be done in P. Now, most people think that this is not true, that you're not going to find an NP complete problem, you're going to get it. But it can't be proved. Not it can't be proved, no one knows how to prove it. No one knows how to find an easy algorithm for 3CNF, for SAT, for the click problem. Nobody knows how to do it. And these problems have been around for 50, 60 years, and still nobody knows how to do it. Conclusion, not conclusion, people think that this means that no such algorithm exists. Okay? Great. Now, I told you last time, and the book does it now, if you have an NP complete problem here, okay, everything reduces to it, and you have another NP complete problem, and you have changed it into that, then this one's also NP complete. Okay? And we did this with 3CNF and click. The problem is, how do you get the first NP complete problem? Okay? So I'll tell you what the first NP complete problem is. We talked about this before. The first NP is what's called the Cook-Levin theorem. The Cook-Levin theorem is proven by two different people. Cook, who came from Canada, Levin, who came from Russia. Okay, and they proved the following theorem: SAT, satisfiability, is NP complete. Okay. The book goes through a proof of it. You're not really responsible for the proof. You're not really responsible for the proof, but I want to give you the intuition of the proof. Okay, I want to give you the intuition of the proof. The intuition is as follows. I want to convert any hard computer problem into a logic problem. Okay? I want to convert any hard computer problem into a logic problem. That's what this says. SAT is NP complete. That means any hard computer problem, any hard NP problem can be changed into a SAT. Question: what's a computer made out of? Answer: it's a bunch of logical circuits. Computers do logic. They're engines of logic. They do and or, and arrow, and not, and implication, and double implication. That's what the ALU does, arithmetic logic unit does. They do all types of logic. If this transistor is on and that transistor is on, then turn this transistor is on. If this is if the person presses this button and then they press that button, and you send this data to here, etc., etc. That's all logic. Okay? So any hard problem that a computer can solve is already a logic problem. Okay? And what Cook and Levin did was they showed you how to express it as a logical formula. Okay? So that is the first hard NP problem. And what you do in section 7.5, which we are not responsible for, what we're doing in section 7.5 is show that other problems come off of SAT. So I just want to not do it, but I want to show you, we're not doing section 7.5, but I want to just show you in section 7.5 what you have is, you have NP. We already showed that SAT is NP complete. What you further on do is you show that click is harder than SAT. Vertex cover is harder than SAT. Hamiltonian path, which we saw, is harder than SAT. Harder than or equal to. It turns out that all these different problems are equal. The last one is subset sum. All these other problems, SAT can be turned into all these other problems. Every problem can be turned into SAT. That's what Cook-Levin theorem says. Every problem can be turned into SAT, but SAT can also be turned into these problems. Conclusion, these problems are also NP complete. Great. Now let's talk about how we make $1 million. Because the idea is as follows. In the year 2000, there was a man named Clay Institute, who wanted to push mathematics. So what he did was he picked 7 problems, him and a bunch of experts picked 7 hard math problems, and said, look, if you can solve any of these problems, I'll give you $1 million. Okay? And one of those math problems is the P is equal to NP problem. Now, you might say that's a computer problem, it's not a math problem, but it can be, it's so important and it can be so exactly stated that they considered it a math problem. Now, there's 2 possible solutions to the P is equal to NP problem. One is that P is equal to NP. In other words, even the hard problems, there's a trick to it. And the other is, here's NP and here's P. P is a subset of NP. They're not equal. This says that there are tricks to do the NP problems. Tricks, polynomial algorithms to do them. This says there are no tricks to do them. You have to do them. The NP problems are really harder than P. Now most people believe this is to be true. Again, I gave you a sociological reason, because for 50 years people have been looking for tricks and they couldn't find it. By a trick I mean a polynomial algorithm. So you have to solve this in order to make $1 million. There are 2 ways of solving it. One is pick any NP complete problem. Okay, I want to show you how to solve it this way. Pick any NP complete problem, find a polynomial algorithm for it. Then you'll show that this is true. That's one way. Okay? Because if this is NP complete, and you could show that it's a polynomial algorithm, then everything falls into polynomial, because everything reduces to this, and if this is a polynomial algorithm, everything becomes a polynomial algorithm. Okay, that's one way of doing it. This is showing that this is, now I got to tell you, that's a pretty hard thing to do, because for 50 years people have been looking for polynomial algorithms for these hard problems and no one's been able to find them. Okay? There's another way to make the $1 million. By the way, that probably doesn't work, but I can't prove that. Another way of making the $1 million is as follows. Pick some problem out here and prove that there is no polynomial algorithm for this algorithm. Prove that this problem is outside of P. This is those problems where there's polynomial algorithms. This is the problem where show that this problem does not belong in here. How do you do that? You have to show that no polynomial algorithm can solve this problem. I don't know how to do that. I don't know how to show that something does not have a polynomial algorithm. This whole book shows you how to solve problems using how to solve problems. I don't know how to show that there's no algorithm to do something like that. If you figure that out, you'll make $1 million. Anyways, that is the end of theoretical computer science that we're doing. Okay, we're not responsible for section 7.5. You've seen formal language theory. What can weak computers do? Computability theory. What can computers do and what can they not do? And you've seen what computers can't do efficiently. That's chapter 7. Okay, so you've got a little taste of all of theoretical computer science. There are other classes given in theoretical computer science which build off this one, and it's actually quite interesting. Okay? Have a wonderful break. Take care.